Hello, I'm José Santos, and my thesis is on Glasma Role and Jet Quenching Effects. One question we seem to persistently end up asking is, what is stuff made out of? And every time we get an answer, we want to know if the building blocks we found are fundamental or made of smaller blocks still. Most of the scientific consensus on what we believe are the fundamental particles is agglutinated in the standard model of particle physics. It proposes this set of fundamental particles and uses quantum field theories to describe their interactions. Specifically, the strong sector contains the particles that feel a strong force, and its quantum field theory is quantum chromodynamics. The 6 quarks in the gluon make up protons, neutrons, and many other composite particles. It is the strong force that keeps the nucleons in atomic nuclei together, for example. We are not able to observe free quarks in gluons, as they always come together and form composite particles. This is called color confinement. In wanting to study QCD experimentally, we take a usual particle physics approach. We smash particles made of quarks and gluons together and study the pieces. At colliders, we can accelerate them to close to the speed of light, have them collide at points equipped with detectors, and identify the produced particles and measure their energy. The accelerated particles can be the nuclei of heavy elements such as iron, gold, and lead. They're called heavy ions, and at the LHC, they are accelerated to a Lorentz factor of up to 2500, becoming more like thin disks than spheres. 2 incoming disks meet and collide. The enormous energy densities generated allow reaching exotic states of matter. By time 1 Fermi over C after the collision, a medium is created where quarks and gluons exist unconfined, the quark-gluon plasma. This medium is well described as a strongly coupled fluid with very low viscosity and recreates the conditions of the very early universe. This plasma droplet is both tiny and short-lived, so it can't be observed directly, but we can study quarks and gluons which were deflected in the collision and cross the plasma. We call these particles hard probes. Before they can reach the detectors, they turn into a shower of hadrons, a jet. The loss of energy of a jet from crossing the plasma is called jet quenching. But what about the influence of the medium before it becomes the quark-gluon plasma? In modeling this pre-hydrodynamic stage, a good starting point would be the already existing models for the incoming nuclei themselves. The protons and neutrons in nuclei are made of 3 valence quarks and a sea of gluons and quark-antiquark pairs which constantly pop in and out of existence from interactions between the quarks. At the energy scales we're interested in, the low momentum, short-lived gluons dominate the interactions with the hard probe and are saturated, or tightly packed, in the nucleon. The color glass condensate formalism makes use of all this to enable approximations which allow an analytical treatment. When we use it to model the pre-plasma stage, we call that stage glasma. The glass part comes from an analogy with what was thought to be the behavior of glass, fluid-like at long time scales and solid-like at short ones. Analogously, the low-momentum, short-lived gluons are treated as dynamic fields, while the high-momentum, much longer-lived quarks and gluons become static. Furthermore, since the dynamic gluons are saturated, quantum effects become negligible, which enables their treatment as classical fields. These fields obey the classical Yang-Mills equations, which are like the QCD equivalent of the Maxwell equations. As for the static quarks and gluons, they come in as the static sources. This provides a framework which we hope to use to predict how much the glasma stage influences measurable jet quantities and let us learn more about QCD.